So this is going to be our second lab dealing with gas laws, and we're probably fairly familiar with it now, right? So one of the unique properties of gases is that they take up such a huge space, right? Because the vast majority of space or volume, when you consider a gas, is actually empty space. It's those molecules zipping around that actually creates pressure. And there's such huge distance between individual molecules that we, for shorthand reasons, consider them to be independent actors. And that's why we call the gas law an ideal gas law. What is an ideal gas? What's unique about an ideal gas? What are some of the properties of ideal gases? Well, like noble gases, or, basically we treat gases as so-called ideal gases when we derive the gas laws. So what are some of the assumptions we need to make when we're talking about ideal gases?
That the gas particles don't take up any space.
Yeah, that's one. That for all intents and purposes, like I was saying, if you look at like a cylinder full of gas, the vast majority, like the space in there, like I said, is empty because those gas particles are so small and the distance between them is so great that realistically, 99.999 and so on of that space doesn't have anything in it. So we sort of basically consider, that individual gas particles don't take up any volume, which isn't exactly true, obviously, right? I mean, they must take up some volume, but a very, very, very small amount. So that's one. What's another one we think about as far as ideal gases go? There's basically one other big one.
That they're not attracted to each other.
There you go. Exactly. Yeah, that they don't have any interaction. So we consider that since there's such vast amount of space between individual particles, that they don't really come together and interact. And that's not exactly true, because everything in the universe is somewhat attracted to every other thing in the universe. There's always going to be some amount of interaction. And the gas laws tend to break down under conditions where particles are drawn together, like under extremely high pressure. Gas particles are pushed together so that they actually physically interact with each other, or at extremely low temperatures where they're not really moving much, and so come into contact more frequently than when they're moving around at high speed. So those are the sort of physical behaviors we attribute to ideal gases. And as it says here, no actual ideal gas really exists. Helium is probably as close to an ideal gas as we're going to get, because it's so small and it doesn't really have much interaction with other particles. So it's pretty close to an ideal gas, but even helium isn't completely ideal. So the other thing that an ideal gas does is that it has these linear relationships between pressure and volume and number of moles and temperature. So that, and these things are all brought together, of course, by R. R is the number that relates all those things to each other. So what are some of the things of these are some of the assumptions or some of the things we've learned over the past. And this is actually the law that we're going to be dealing with today. I've sort of told you before that I don't think much of Avogadro's number because we don't really use it much. This is another thing that Avogadro came up with, and we use this one a lot. He was the one who determined that if in a reaction you make twice as many moles of a gas, the volume that it occupies is exactly twice as much. If you make 3 times as much gas, it occupies 3 times as much volume. So he was the one that determined when you have the temperature that doesn't vary and the pressure that doesn't vary, then equal volumes of gas contain equal numbers of particles, or moles. And so what he did reactions, like I said, that if they produced 0.01 moles, he would look at the volume 1, and determine what that volume was. And that's exactly what you're going to be doing today, is making a known amount of gas in moles and determining that the volume it takes up. But if he did a second reaction that produced O2 moles, the volume that it took up would be 2 times that volume. And he showed that that is a linear relationship. And so we're going to be using that law today in our lab. What gas are we going to be producing today?
Oxygen?
That's right. We're going to be producing oxygen. So we need to determine how many moles of oxygen we're going to create. And then we're going to measure the volume of gas that actually is under the constant temperature. We're not going to change the temperature in the room that we're doing the experiment. And the atmospheric pressure probably isn't going to change terribly during the experiment either. So those two will be fixed. And if those two things are fixed, we should be able to determine the relationships. I'll show you how to do that in a minute. So this is why we can come up with a standard molar volume, because if we make the assumption that the gas molecules don't really take up any space and that the relationship between moles and volume is linear, well, then 1 mole of any gas should take up the same volume. And we see that it's pretty much true, that helium and nitrogen and oxygen, as long as we have 1 mole of them, they'll take up the same volume. And that's roughly 22.4 liters of volume at standard temperature and pressure. So for gases, what's the standard temperature and pressure? What's the standard pressure? That one's pretty straightforward.
1 atmosphere.
1 atmosphere. Yeah, 1 atmosphere of pressure. And the standard temperature for gases is slightly different than what we think of as standard temperature for reactions. When we're doing chemical reactions in the lab, standard temperature and pressure for chemical reactions is actually 1 atmosphere and 25 degrees C, because that was considered the standard room temperature. It's a little warmer than most room temperatures we're used to now, but for gases, the temperature is different. What's the standard temperature for gases? It's right on the slide if you can read it.
273.15 kelvins.
Yeah, it's 0 degrees C, 0 degrees Celsius. Now, I don't know why 0 degrees Celsius was considered standard temperature, but it is. So I think probably because a lot of reactions involving gas were done with ice water. They were displacing ice water, so the temperature of ice water is 0. And so maybe that's why, not sure. But that is the standard temperature and pressure for gases. So at that temperature and that pressure, 1 mole of gas takes up 22.4 liters of volume. Now you'll notice that with helium and nitrogen and oxygen, the same number of moles, but the masses are all different. So the densities of each one of these gases is going to be different too, because density is in grams for gases anyway, grams per liter. So the density of helium is going to be smaller than the density of oxygen because the mass is less, but the number of particles is the same. So the mass is just a reflection of the mass of the individual particles. Okay, so here's our ideal gas law, good old Pivnert. So if we're going to have to, this is the accepted value of R. So when you're deriving R, we just rearrange this formula to put R on one side and everything else on the other side. So R is going to be equal to P times the volume divided by N times the temperature. And so you should, when you come up with your value of R, it should be fairly close to this, 0.0821 atmosphere liter mole kelvins. So that is what we're going to be doing today, keeping pressure constant, keeping temperature constant, and looking for the relationship between volume and moles, okay? Now this is the setup. So fairly straightforward setup. Hopefully everyone has all this stuff ready. It's going to be kind of messy, so I would recommend getting like a pie tin or something to put under the beaker here, because we're going to fill it with water right up to the top. And then we're going to fill up this cylinder with water right up to the top, and then turn it upside down and insert it into the beaker. And believe me, water is going to splash all over everything. So either have a bunch of really thick towels, or I'm going to be using a pie tin to collect any spillover. So we're going to be generating gas in this container here. And this is the reaction. And so we're going to be generating gas in this container. Oxygen then flows through this tube and then will bubble through the water. So what we want is this cylinder to be completely filled with water, and then the gas will actually push the water out of the cylinder as it fills from the bottom, which is now the top, and the amount of gas will continue to increase as it pushes water out, and then we just read the volume. So this is the reaction. So remember, when we need a balanced reaction. Anytime we're calculating moles of anything, we need a balanced reaction. So what is H2O2?
Peroxide.
Which peroxide? Because this is peroxide, O2 minus. That's the peroxide ion.
Hydrogen peroxide?
Hydrogen peroxide, right? There's lots of peroxides. This is the most common one, hydrogen peroxide. Everyone has this in their house, probably, in their bathroom. So this is the reaction. So what kind of reaction is this? Remember when we did all the different reactions? We did synthesis and decomposition and single replacement and double replacement and redox and all those different reactions. What kind of reaction is this? Right, Amanda says decomposition. She wasn't sure, but she's right. Decomposition, because we take one molecule and then it splits and breaks down into two. And so the two molecules that hydrogen peroxide is going to break down into is water. That's going to remain a liquid, right? Because it's at room temperature and 1 atmosphere. And at room temperature and 1 atmosphere, water is generally a liquid. And oxygen is a gas. So we got a liquid and a gas. So we're going to collect the gas. The water will stay behind in the bottle here when it decomposes, and the gas will move through the tube. So this is a catalyzed reaction. We're going to be using a catalyst. What does a catalyst do?
It speeds up the reaction?
Right. In general, a catalyst speeds up the reaction. In this instance, we're going to be using an enzyme. An enzyme is a biological catalyst, generally a protein, Protein is a chain of amino acids that folds into a particular three-dimensional shape. And this particular three-dimensional shape catalyzes the decomposition of peroxide into water and oxygen. And it's incredibly important. You have this enzyme inside you. Pretty much all organisms have it, because peroxides are extremely reactive. And that's why you basically overwhelm when you have, like, bacteria and stuff in a wound. You want to kill them. And so you overwhelm them with a really high concentration of peroxide, and it basically wipes them out, because the peroxide molecules oxidize everything in their path and basically, wipe them out. But small concentrations of peroxide, you do not want those in your body. You want to break that down into non-reactive molecules like oxygen and water. And so you have and this enzyme is called catalase. It is one of the very first enzymes discovered. In fact, it was discovered by the same person who discovered peroxide in the first place. He noticed that this was broken down very, very quickly, and by biological things. So if he had just peroxide in a container, it didn't break down very quickly. But if he added anything biological, it sped up the reaction. And then he isolated this particular enzyme. So is this part of the reaction? Do we consider the catalase part of the reaction?
No.
No, it isn't, right? Because it isn't part of the products. It isn't part of the reactants. We would put it right here. We would put it on top of the arrow to show that it is catalyzing that reaction. It's making it go much, much faster than it normally would. But it doesn't actually, it isn't part of the reaction. It itself isn't changed. That is part of being a catalyst. It isn't changed from the beginning of the reaction to the end. It might be changed in the middle of the reaction, but at the end of the reaction, it goes back to being whatever form it was before. So it isn't either a reactant or a product. So we don't write it into the equation. So this gives us the molar ratio of hydrogen peroxide to oxygen. And so what's going to be our molar ratio of hydrogen peroxide to oxygen?
Two to 1.
Right. For every 2 moles of peroxide, we're going to make 1 mole of oxygen. And so we're going to calculate the number of moles of peroxide, because we have a bottle of peroxide. We know how much peroxide we're going to add to the reaction. And if we could figure out how many moles of peroxide we have, we can calculate how many moles of oxygen we should get. So here's our PIV nerdy goodness here. So if I take PIV nerd and I want to solve for volume, because that is really that's what we're going to be measuring, right? We're going to be measuring volume. So if I want to have volume by itself, I divide both sides by P. And so V is going to equal nRT divided by P. So we're going to be plotting the volume, because that's what we're going to be measuring. Now, if my temperature doesn't change and my pressure doesn't change, then really, so T is going to be a constant. P is going to be a constant, and we know R is a constant because that's the definition of R. It's a constant. And so we can see right away that there's going to be a linear relationship between volume and moles, right? So if we calculate the number of moles, we should be able to see how many moles are involved in taking up that particular volume. Okay, so I want you to remember this. This is what the relationship is going to be. So when we plot this out, we're going to have, which one is going to be our X and which one's going to be our Y when we plot our results. Which one is the dependent variable? Which one is the independent variable? Remember, the independent variable is the one that we can vary. The dependent variable is the one that can't. That's dependent on the independent variable. So what's the independent variable? What's the one that we can determine and change?
Volume.
No, because we're measuring the volume, right? We don't know what the volume is going to be. We start our reaction and we see what the volume is, but we don't determine it. We don't predetermine it beforehand. But there is something we do predetermine before we start the reaction. What's that?
So then it would have to be moles.
Moles, exactly. So by using a specific amount of hydrogen peroxide, we're going to measure or calculate the number of moles of oxygen that produces. So we're going to have moles down here and volume over here. And it should be a linear relationship. We should get a linear relationship between moles and volume. Okay. So I'll just go over quickly how you're going to go ahead and do this. So you'll have a thermometer to determine the air temperature wherever it is you're doing it. You could also look up, like we did before with the airbag experiment, look up what the atmospheric pressure is wherever it is you are. And generally, if you remember when we did that last time, you're going to get the atmospheric pressure will be given in inches of mercury, which isn't terribly useful. So you'll have to convert that to millimeters of mercury. And then remember that 1 atmosphere is equal to 760 millimeters. That is the pressure you're going to be using to determine your R. It should be pretty close to 1. I don't imagine there's going to be much difference between where I am in Pacifica and where you are, but there could be slight differences in pressure. So we fill up our graduated cylinder completely with water. We fill up our beaker completely with water. And when I show you the setup, I'll show you how to actually do this. It's a little bit tricky. So we're going to have that dropper, which is right here, and it has a little end on it that we're going to push a hose down. Make sure that it's pushed down pretty well because we want it to be gas tight. And then we're going to put our thumb, or maybe 2 fingers or whatever you've got to be able to cover the top of the 50 ml cylinder with the tube in it, turn it upside down, and then put it into the water. Try not to let any of the water out. If you do leak out a little bit of water, not a problem. If there's an air bubble up on top here, just measure what the size of the air bubble is. If it's 10 mils, that is going to be your initial volume. And then whatever more volume gets added from the gas, that will be your oxygen. So the first 10 mils is air. Anything subsequent to that is going to be the oxygen that you make. So like I said, record the initial volume of gas, and then we're going to weigh out some yeast. So notice it says here, weigh out 0.1 grams of yeast. It doesn't say 0.10 grams or 0.100 grams. Is it important to get the amount of yeast super precise? Why do you think they just say 0.1 and not 0.10 or 0.100?
Because they want it exact.
No, they don't, because they say 0.1. Basically, all 0.1 means is that it's not 0 and it's not 0.02. So it doesn't have to be very, very precise. Why is that? You have to be precise about everything else. You need to be precise about the amount of hydrogen peroxide you add. You need to be precise with the volume of the oxygen you collect, but you don't have to be very precise with the amount of yeast added. How come?
Because the catalyst.
Because that's the catalyst, right? Why is it important that we determine how much catalyst is there?
Because it doesn't participate in the reaction.
It doesn't participate in the reaction. That's one thing. What's the other reason? And basically, what does a catalyst do? Why are we adding the catalyst in the first place? Right, Francesca. It speeds up the reaction. So if we have twice as much catalyst, it just speeds up the reaction a little bit more. But we're not going to get any more or any less product. We're just get a little faster. So you need to have enough catalyst to speed up the reaction. But as long as one molecule of catalase will basically do a couple million molecules of hydrogen peroxide into O2. The turnover is so fast that just a tiny amount of yeast will basically catalyze the reaction like that. So any more, it'll speed it up a little bit, but it really won't make that much difference. So it's not terribly important how much you add, as long as you have some. So around 0.1 grams. So if you have a little bit less or a little bit more, doesn't really matter. If you have a little bit less, it may take an extra couple seconds for the reaction to finish. If you have a little bit more, it may happen a few seconds faster. So we put the yeast into our little drop bottle. It's about 15 mils. We measure 1 mil of hydrogen peroxide in the cylinder. Record the exact volume. If it's 1.1, record that. If it's 1.2, record that. That volume needs to be precise. Then this is what you have to do really, really fast. So we have the top of the bottle, sort of like the little nipple with the hose already attached to it. And you got to put that sucker on as quickly as possible, because the minute you add or actually more like the microsecond you add the hydrogen peroxide, that reaction starts. And so gas is being produced and you need to put that cap on as quickly as possible. I'll take you through how to do that. And then just let the reaction proceed. And bubbles will start to form, and you'll see the bubbles displacing liquid in the 50 mil cylinder, and you just let it go. Just let it keep going. Every once in a while, you may want to shake the dropper bottle a little bit just to make sure you're mixing the peroxide with the yeast. You want to make sure that all the peroxide gets reacted. And then when no additional gas has been formed for about a minute or so, you're done. And then just record, and this will happen fairly quickly, like 1 or 2 minutes. And then you just record the final volume of gas in data table 1. So what we're going to do is start with 1 mil. So we're going to do 1 mil. We're going to do that twice. And then for the next, that's our first 2 trials, trial 1 and trial 2. So we have 1 mil twice. And then we're going to do 2 mils, 3 mils, 4 mils. So you have a total of 8 trials. So you're going to be doing these in duplicate. And then you'll plot. You should have 8 points on your graph when you plot them. Don't average these, your results, just plot them all. So like, the more points you have, basically, the better the fit of your line will be. So we should get roughly the same volume of gas for these two, these two, these two, and these two. Your final volume should be pretty close to each other. Then need to do some calculations. So we can run through that stuff fairly fast. These don't take very long to do. Make sure you wash out the bottle in between trials. You don't want to have any leftover hydrogen peroxide or yeast in there. Just, you know, rinse it out with water a couple times and it's good to go. So check what the concentration of your peroxide is. It should be 3%. So 3% is weight to weight. It's mass to mass. So it's 3% of the mass of the solution is hydrogen peroxide, meaning that for every 100 grams of solution, 3 grams of that is peroxide. So we're going to assume that the density of the hydrogen peroxide is the same density as water. What's the density of water in grams per mil?
1 gram per milliliter.
Right. That's one of the nice things about the metric system that makes some of these things really easy to remember. So the density of water is 1 gram per milliliter. So if we have 100 milliliters, we also have 100 grams. And if we have 3% of that is hydrogen peroxide, for every 100 mils of hydrogen peroxide, we should have 3 grams of it. So you can figure that out. If we have 100 mils, we have 3 grams. If we have 1 mil, we have 1/100th of that. So 0.03 grams. And then so on and so forth for 2 mils, 3 mils, 4 mils. So that's how many grams we're going to have. Now, we're not interested in grams, right? Because we're chemists. We don't care about grams anymore. We can measure grams. What is it we really want in order to do chemical calculations?
Moles.
We need moles, right? Grams aren't going to help us. We can measure, grams are helpful because we can easily measure grams with a balance or a scale, or we can determine volume very easily and convert that to grams using density. But we don't really use grams when we're calculating reactions, for instance. So we're going to need to take grams and convert that to moles. And they give you the molar mass of hydrogen peroxide at 34.01 grams per mole. So you're going to take the number, you're going to measure the volume of the hydrogen peroxide. You're going to convert that to moles of hydrogen peroxide, or grams of hydrogen peroxide, and then finally convert that to moles of hydrogen peroxide. And then once you have moles of hydrogen peroxide, what's the last calculation you're going to do in terms of moles? What do moles of hydrogen peroxide allow you to determine?
Moles of oxygen.
Bingo. Yeah, moles of oxygen. So you have to go back to the balanced equation and see, well, I had 1 mil of hydrogen peroxide, meaning I had this many grams, meaning I had this many moles of hydrogen peroxide. All of it's going to get converted to oxygen. How many moles of oxygen is that? So then you'll have moles of oxygen and you'll have volume, and you'll be able to see what the relationship is. So you're going to take, oh, go ahead.
Are we not measuring the amount of oxygen through the cylinder? We're calculating it through the balanced equation?
Right. You're going to be calculating moles of oxygen. So this you calculate. Moles of oxygen is going to be calculated. Volume of oxygen is going to be measured.
Okay.
Because we don't know what that's the whole point of the experiment. We don't know what the volume of oxygen. I mean, we can probably calculate it using R. But let's say we don't know what R is. So that's what you're going to do today, is you're going to determine what R is. What is the relationship between the measured volume of a gas and the calculated number of moles? That's what you are actually going to do. So when we plot this stuff, this is going to plot. And we've already, we sort of already broke this down. What goes on the x-axis again? What are we going to plot?
Moles
Moles of what?
of oxygen.
Right. So we're going to determine moles of oxygen down here. And what are we going to put on the y-axis?
Volume of oxygen
In what?
in milliliters.
So we're going to have volume of O2, but what unit are we going to use? And remember, we're determining R. What are the units in R?
Oh, in liters.
Liters, right, because the units for R are atmospheres, Kelvin, moles, and liters. So we're going to need to convert our temperature, the room temperature, to Kelvin. Hopefully you know how to do that, right? This is going to be moles of oxygen. This is going to be our atmospheric pressure. And this is going to be our volume of oxygen that we collect. We're going to measure that in milliliters, but we're going to need to convert that to liters. So when we get our plot, the slope of that line, remember, we're going to get a y equals mx plus b. What should the y-intercept be for this experiment? Remember, the y-intercept is where, when x equals 0, what y should be. So if x equals 0, if we have no moles of oxygen, what should the volume be?
0.
Should be 0, right? It should be, and that's not going to be exactly 0, but it should be pretty close. If your y-intercept is a big number, like 5 or something, you've probably done something wrong. You probably put the wrong numbers in. B should be pretty close to 0, maybe a little bit negative, maybe a little bit positive, but it should be a really small number. And M, the slope, will be liters divided by moles. So remember, if PV equals nRT, and we are plotting moles is X and volume is Y. So let's isolate Y will be volume, and this will be nRT divided by P. So the slope, this is the slope here. So this is Y. This is M, and N is X. So the slope of your line is going to be RT divided by P. So your slope, remember, you're going to have to put the temperature in and the pressure in order to determine what R is. So you're going to have to divide by temperature and multiply by the pressure in order to convert this slope into R. Okay, I'll go over that with you before the end of the experiment. In fact, I can do that now. I'll show you. Now, I did this experiment with another class earlier, and I'll show you my excellent data. All right, so hopefully you can see, everyone see the data here? If I plot it?
Yeah.
Okay, you're all seeing it, good. So, oops. Wait a minute. I'm not seeing it anymore. Where did it go? There it is, okay. So I did 4. I did calculated my moles of hydrogen peroxide, and I measured the volume. And this was the slope I got. So you can see that the B or the y-intercept was really, really, really small. So I felt pretty good about that. The R squared tells you how, if it's a perfectly linear relationship, R squared should be 1. And you can see it's really, really close to 1. So it means it's a good fit. And this was the slope of the line. Now, what mistake did I make here? I made a mistake. Anyone see what the mistake was? What did I do wrong in this plot?
You only have 4 points.
What's that?
You only have 4 points.
Well, yeah, I mean, I should have 8, but you know, I was just doing the demonstration. I wasn't going to do the whole experiment. I did something wrong. I'm a bad man. Is it the X, Francesca asks, is it the X value? No, there's no, I mean, the slope is the slope. That's actually, these are good results. I mean, R squared is really close to 1. So notice that I have errors on both sides of the line. So this one's a little lower than the line. This one's a little above. This one's a little below. So my errors are balanced off. But I take that result anytime. So that's not a problem.
Is it because you use moles of peroxide instead of moles of oxygen?
Exactly. Excellent. Yeah, I was in a hurry because this doesn't tell you how many moles of gas. R is a gas constant. You need to have moles of gas to volume of gas. So I screwed up. This should be moles of O2. And remember, for every 2 moles of peroxide, you get 1 mole of O2. So these numbers should be half of what they actually are, meaning the slope should be twice as much. And so if you take the slope, multiply it by 2, and then I subtracted divide it by the temperature, multiplied by the pressure, and I think my final value of R was 0.073. Which is pretty good considering you should get 0.0821. So I had like a 10% error. So that's one of the things you probably should put in your report is how far off are you from the actual value of R. And if you can get an error of like, you know, less than 25%, I think you're doing pretty well. So it's just a matter of doing your calculations carefully, measuring the volumes carefully, and you know, basically getting the setup done properly. So yes, you should have 8 points on that line, but it should look pretty similar to that. And your slope should be somewhere around 20, 21 in that region. And look for your R squared value. If it isn't close to 1, then you may want to throw some of those points out. Like for instance, if you have 7 points that are all pretty close to the line and 1 that's down here, well, that's an outlier. You can toss that, and your R squared value should get much better. All right. So does everyone have their stuff ready to go? I'll give everyone about I don't know, 10 minutes or so to get all your stuff together, and then I'll move over and we'll start working on the actual experiment. Okay. Any questions before we get started?
Is it okay if my 10-year-old sister helps me?
Of course. I have my 11-year-old son help me all the time. Just make sure she has goggles on. Okay. Yeah, because you won't need gloves for this one. For the next one, you certainly will. I was doing the vitamin C determination last night, and there's a dye in it that basically, I think my fingers are still a little bit blue from it. So, but this one, I mean, you know, dried yeast and a little bit of peroxide isn't really going to hurt anybody. So, but you definitely want to have, you don't want to get peroxide in your eyes. That's bad news. So I'll give everyone 10, and then we'll come back and we'll do the experiment, all right? Okay, see you in a minute. Okay, hopefully I'll be seeing more of you. There's Lance. Good to see you, buddy. Okay, so I'll sort of bring this down a bit so you can see what's going on. So I've got my, you can see I'm using a pie tin because I don't want to make a big mess. So what I'm going to do is fill that up with water. Okay. Then I take my graduated cylinder. I'm going to fill that bad boy with water as well. Okay. Now this is the tube that, so you have one of these plastic tubes, and this is the little piece that fits in the top of the dropper bottle. So you should have this piece. So this fits into the dropper bottle and snaps like that. So basically the dropper bottle should just look like this, look like that, and just push the tubing down a little bit. So when you pull it, it won't come out terribly easily. And then to pull the stopper out, you sort of bend it like this, just sort of, it comes out fairly easily. Don't pull it out because you might pull out the tube. Just sort of bend it a little bit, and it pops out. So the end that doesn't have the cap, this end, this is the one we're going to put into the cylinder filled with water. We just push it in there. And then this is where it gets a little bit messy, because we're going to want to have this filled with as much water as we possibly can. So it might get a little messy. And then put your thumb over it. Turn it upside down and put it into the, if you do it fairly quickly, you don't spill much water. So you can see that I may have a tiny little, I have a tiny little bubble in there, but not much of one. You can see there's a, I don't know, you probably can't even see it. There's a little tiny bubble. So that's going to be a small error in volume, but you know. And then make sure that when you put it into the water, that the tube has not come out. And just let it sit there. So has everyone managed to get that part done? Because that's the most critical part of the experiment, is making sure you don't get any air bubbles. And if you do, just measure the volume. Like for instance, if you have 5 mils of air in there, that's fine. So you start with, your initial volume will be 5 mils. The second volume would be like, 26 mils. The difference is 21. That's going to be your volume of oxygen produced. So next, I want to take my yeast. So you get you should have your little package of yeast here. Hi, Nicole. So take one of your weigh boats. Make sure your scale is in grams. Last time I did this, it was in carats, which wasn't terribly helpful. So make sure it's in grams. Put your weigh boat on top of it. It should be about 2.4 grams or so. And remember to tare that so it goes back to 0. And then about 0.1 grams. It doesn't, like I said, it doesn't really matter. Around 0.1. If you have a little bit more, no biggie. A little bit less, no biggie. But I don't think you want to have less than like 0.05. The reaction just might take too long. So I've got like 0.14, which is fine. So remember that one of the nice things about the design of these weigh boats is that when you're transferring your yeast, you can see I had a little bit there, you can just fold it up and it sort of makes for a nice little method of transferring it to the tube. Just tap it in there. Now you should be measuring the temperature. You should have your thermometer nearby. The temperature here is, let me have a quick look at it. It is 15, 16, but 17.5. So remember, you should have 3 significant digits, 3, to your temperature. So if it's exactly 15, you determine 15.0. If it's halfway between 15 and 16, it's 15.5. If it's like 3/4 of the way, 15.7. You always estimate, remember, when you're measuring these things, you always estimate that last digit. Unless you've got a digital, if you have a digital thermometer, like a meat thermometer, that's even better. That'll give you the precise temperature. In fact, I have one of those. I should be using it for this.
Do we need to measure the temperature for each trial, or do we just use the same one?
I would have a look at it. I mean, it probably won't change much. I wouldn't imagine, unless you have a window open and there's like a breeze blowing through. It really shouldn't change very much.
Okay, because in the second data table, it doesn't give us a spot for like each individual trial. It's just one like long.
Right. So I would just keep an eye on it. If it does change, then you would, take that into consideration, but it probably won't.
Okay.
And even if it does, a change of like 1 Kelvin really won't make a huge difference in the volume. Probably the error in measuring the volume will probably be more than the error of 1 degree. So yeah, you're probably right. I mean, you just measured at the beginning, you're probably good.
Okay, thanks.
So then, now I've got my yeast and my little tubey tube here, my eyedropper. So now we need to measure 1 mil. And so for this, they're having us use this 10 mil cylinder. You should have your 10 mil cylinder. I think you could probably also use your 5 mil syringe if you have a 5 mil syringe, and you should have one of those in your kit. Either way, measure out 1 mil. Now, if you have a little bit more than 1 mil, then measure that accurately. If it's 1.1, write that down. If it's 1.2, write that down. Because it's not as important to have exactly 1 when you're plotting as to have the actual accurate volume. All right, so I'm going to see what my volume is. I got more than 1 here. Wow, I got more than 2. I got 2.8. Yikes. Okay, that's more than I expected. So mine's going to be 2.8. So you're going to want to have 2 runs with around 1 mil, 2 runs with around 2 mils, 2 runs with around 3, 2 runs with around 4. So that's why I don't want you to average the results, because like when you're doing 4 mils, maybe for the first run, you had 3.9 mils, and for the second one, you had 4.1. That's totally fine, as long as you accurately determine that volume. You obviously then can't average those because they're not, the results won't be from the same volume. So don't average them. Just plot each individual run. So you take your hydrogen peroxide. Now this is where you're going to need to have your tube ready. So I have my tube ready to go because this reaction is going to start, and it's when it goes very, very quickly. So I'll dump this in and then put the cap on as quickly as I can. So here we go. And then put the cap on and snap it in place. There we go. And so you can see it's starting to foam. And then just give it a little tap to mix it. You see the bubbles forming. And eventually the pressure should be enough in the tube to start bubbling. Bubbling up through the liquid. And you want to mix it because you can see I've got a big clump of yeast there. So I want to mix that up. For some reason, I'm not collecting any gas yet. I should be collecting gas. Unless I have a leak somewhere. Oh, there it goes. Whoa. And my reaction pretty much happened all at once. I think what happened is that the pressure had to get high enough in this tube to displace some of the water that was already there was already water in the tube. So the pressure had to get high enough to displace that. And when it did, it just went all at once. So I'm just going to keep mixing it. You see, I still keep getting a few bubbles coming out. That's interesting. I haven't that hasn't happened before, where I got all the gas at once. I was worried that maybe my hydrogen peroxide was old or something. So I'm just going to let it sit for a minute or two and see if any more gas is produced. And then this is, so this you can, I don't know if you can see it, but so I've got, yeah, you can see that. So I've got water up to there, and then gas from the top. And so I just measure the volume. I just turn this around, and you just read off the volume from the top to the bottom. So I had a tiny, tiny gas bubble at the beginning, but pretty small, didn't really take up any volume. So my final volume is going to be 10, 20, 20, 29.1 mils. I don't see it. I'll keep mixing this, but I don't think any more gas is being produced. So in no more gas is produced, what does that mean for the hydrogen peroxide that was in the bottle? What happened? Which one is the, since we have a, what's the sort of limiting reactant here? When does the reaction stop? Right, John. Yeah, there's no more peroxide. It's the only it's a decomposition reaction. So the only reactant is peroxide. So once all the peroxide has been broken down, and we should have a vast excess of catalase enzyme. That shouldn't be limiting anything. As long as you've got your around 0.1 grams, you should have more than enough catalase. So once the peroxide has all been converted to water and oxygen, then the reaction stops. And I'm not getting any more bubbles. So all my peroxide has been converted. So then I just read the volume. And again, with the volume, you're going to want 3 significant digits as well. So if it's exactly 30, write 30.0. If it's in between 30 and 31, where is it between 30 and 31? If it's exactly halfway, you say 0.5. If it's just barely more, you'd say like 30.1, something like that. So mine is pretty much on the line of 29, but maybe a little bit more. So I'd write down 29.1 or 29.2 mils. And remember, you're going to want to convert that to liters before you plot it. So this reaction's done. So I just take the cap off and I just empty this out into waste and just rinse it with water a couple times just to get all the yeast out. So have a little cup or something to dump. I just going to have this little cup to dump all my yeasty beasties into and just rinse it out with water for the next one. Because if there's a little bit of water in there, it doesn't really matter. Water's not really part of the reaction, so it won't slow it down or speed it up. Okay. Now the other messy part is taking this darn thing apart and then doing it again. So now I just refill it to the top with water and go for my second run. Now, if you have any air bubbles in it at this time, it wouldn't be a bad idea is to tap the sides. Sometimes you'll have little air bubbles sticking to the sides of the tube. If you have that, you can just tap it with something heavy, a fork or whatever you got nearby, a spoon, get all those air bubbles up. All right, put my tube in there. Fill it to the top again. Big thumb, and don't let go until you get it under the water. There we go. So this time I got a bigger bubble than I did last time. So I've got about 2.5 mils of air already in here. So whatever volume of gas I collect, it's no, you can, I mean, you can try filling it up with gas, filling up with water again, but it's kind of a pain. So I will just take my 2.5 mils and subtract it from whatever volume of gas I get this time. So again, just measure out your 0.1. Oops.
The initial volume is like the space when you first flip it over, right?
Exactly. Yeah. If you don't have any air bubbles, your initial volume is 0. It's really tricky to get it exactly 0. I've managed it a couple times, but generally you'll have like some kind of a bubble. But it's no biggie, because we assume that since gases don't interact with each other, which isn't really true, we assume that gases don't interact with each other. So if I add 1 liter of one gas to 1 liter of another gas, what's going to be my final volume? Oh yeah, Jean, you can use whatever cup you want, man. As long as you can turn the cylinder upside down in it, that's no worries. So if I add 1 liter of gas A to 1 liter of gas B, what's my final volume? Two, right? Because we assume that those gases are independent of each other. Same goes with pressure. I don't know if you've learned about partial pressures, but if I have a tank of gas at 10 atmospheres, and 3 atmospheres of it is nitrogen, 4 atmospheres of it is oxygen, and another 3 atmospheres is hydrogen, they're all independent of each other. The pressures of each one will add up to the final. All right, so I've got my yeast. Measure out my hydrogen peroxide. All right, so this time I have about, I got about 4.5. That might be a little bit too much. Dump a little bit of it out. Yeah, remember, because I think if you use about 5, if you use over 5 mils, I think that'll completely fill the tube. There we go, that's a little bit better. 3.6. Because all these experiments are calibrated basically so that you don't get, because if you get more than 50 mils of gas, it's going to completely empty the cylinder, and then you don't really know what the volume is. You just know it's more than 50. So 3.6 mils. Let's see what this gets us. All right, pouring it in. Putting the cap on and then mixing. Yeah, one of the keys to doing this experiment is mixing these things. Yeah, so you see, I get bubbles much faster this time because I didn't have an airlock in my in the tube. There was no liquid in there, so it's started collecting much more quickly. So when you're doing your calculations, take your temperature. Remember, you're going to convert that to Kelvin. Take the look up the atmospheric pressure. You can just go to like AccuWeather.com or someplace like that. They'll give you the pressure either in millimeters of mercury or inches of mercury. Convert that to atmospheres, and you can assume that you're going to have the same temperature and the same pressure from the beginning of your trials to the end. So how's everyone's reaction going so far? Are you able to successfully make some O2?
Very slowly.
Oh, it's slow, is it? So was that for the 1 mil?
Yeah, like it's.
Yeah, that one. Yeah, I mean, obviously, the more material you use, the faster the reaction is going to be. So with 1 mil, it's going to be the slowest, and then it should be twice as fast for 2, 3 times as fast for 3, and 4 times as fast for 4. So that looks like it is pretty much done. Yeah, keep mixing it too, Lance. That will also help. Yeah, mine appears to have stopped. So a little more than last time. So 10, 20, 30, 5, 6, 7, 38 and a half. 38.5 mils. So then I subtract my 2.5 mils that I had originally, and that gives me 36 mils. So I think the way that this is constructed, is that it looks like you get approximately 10 mils of oxygen for every 1 mil of hydrogen peroxide. Approximately. So at least with the 2 I've done, that's pretty much what I've got. So that's why I think you don't want to use more than 5, because if you use more than 5, you're going to get more than 5 mils of peroxide. You're going to get more than 50 mils of oxygen. Which means that's exactly what I'm going to do, just for grins. So everyone else whose camera isn't on, I'm assuming you're doing the experiment today, or you're doing it later? Because this experiment is pretty straightforward. You can work. I've done 2 of these in like 15 minutes, so it doesn't really take very long to do. So I'll be curious to see what results you get. I might take all the values and just post them to see, and then average them, see how close. Because if everyone could, if we see errors on both sides, a little bit more, a little bit less, we might average in and get pretty close. And if you want to make bread, you've got all this yeast left over. But I don't know if this is the good for making bread kind or not. Might be the good for brewing beer kind. I'm not sure what kind of yeast it is. So it does say not for human consumption, so okay. Okay, I got 6 mils. So this should make more gas than you could actually collect. Just want to see. Oh, I need to reset my container. Okay. All right, smaller bubble this time. All right.
Kind of sucks that I have to do this 8 times. After like the 3rd time, it's kind of like the novelty is worn off.
Oh, come on, it's still fun. But yeah, I hear you. Oh man, yeah, with six mils of peroxide, it's going like gangbusters here. So I've also got some yeast coming out of the top, which probably isn't the best. There we go. Yeah, I definitely wouldn't recommend using more than 5 mils. It's actually pushing the yeast up through the tube and into.
Found a shortcut. If you clean the bottle with a Q-tip, it goes faster.
What makes it go faster?
You clean the bottle with a Q-tip, so you don't have to
Oh,
wash.
yeah, there you go. Yeah, I don't think it needs to be dry, but It just needs to be free of yeast and peroxide. Okay, so yeah, so it's 6 mils. Yeah, it looks like I got about 60 mils of gas. So yeah, I think it's pretty much right on, because it's definitely above 50. It looks to be about 10 mils more. So I think that's our expected result. Now just have a nice little mess to clean up here. Yeah, so I'll probably post the recording tomorrow. I usually post them the next morning. So is everyone clear on how to plot the data? Would you like me to go over that one more time? Does anybody want a review of the data analysis?
I think I'm good.
Okay.
Yeah, it's really just like the moles of oxygen and the volume of it.
Yeah, but you're going to get so the slope of that line is going to look weird. So it's not going to be even close. It's not even going to be close to R, right? You're going to get some slope like 20 or something. Well, that's not close to R at all. But remember that the slope has both the temperature and the pressure in it. So you're going to want to take that into consideration. So that's where getting the temperature correct is going to change that.
So
So
you have to, like, slope equals RT over P and then solve for R?
I think that was it. Yeah, I think you wind up dividing by the temperature and multiplying by the pressure, because yeah, T will be on the top and P will be on the bottom. So in order to eliminate those, you divide by T and multiply by P, and then that takes out T and P, and that should leave you with just R. So when you do that, yeah, your result should be fairly close to 0.08. If it's like 0.06 or like 0.09, that's great. If you get something way off, then you may want to look for potential errors. Yeah, but even using these fairly primitive methods, I was able to get it like within 10. So I think just as long as you just pay careful attention to the volume of the peroxide you use and the volume of the gas collected. Obviously, those are the only two things we're measuring. As long as you get those accurately enough, then it should be fine. One thing I would want to point out is how many significant digits are there in the concentration of the peroxide?
One?
Yeah, just one. So we're really sort of making a huge assumption that the concentration of the peroxide is 3.0 to even get 2 significant digits for R. So I think just reporting R with just 2 significant digits is more than enough. Because really, if we were going to be scientifically accurate, we would report it to only 1 significant digit because we only have 1 for the concentration. So that could be a big source of error right there. This thing could be 2.6% peroxide. So we could be way off with our calculations. So again, don't get too upset if your value of R is off by like 25%, because like I said, we're making a big assumption with this concentration. It probably is 3.0, but we have no idea whether it is or not. So anyway, so are there any other questions? I will let you go if because we've gone through how to get everything set up. Are there any questions with either the setup, the calculations, or the data analysis? Just going to plow through, Arissa? You're just going to fight that boredom?
Yeah, I'm really bored.
Well, you know, chemistry isn't always fun. It was more fun when we were burning things and making things explode. Yeah, that lab was a lot more fun. We got to blow up hydrogen. That's always fun to do.
It's very repetitive.
Mm-hmm. That's why when I was doing experiments like this at UCLA, I had a robot to do my experiments for me.
I should just build a robot then.
Because instead of doing 8 experiments a day, I was doing like 256 experiments a day. And yeah, that gets a little tedious if you're doing it by yourself. So I had a robot do them.
Is there any way that you could extend experiment 11 till tomorrow?
Oh, okay. Yeah, that's not a problem.
Thanks. It was just because there's like 2 labs due today, and then the exam, and then the pre-lab, and it was like
There was 2. Oh, that's right. We had we pushed one over. Yeah, that's no problem.
Thank
I got
you.
some water on my keyboard. Oops. Yikes. Yeah. I told you it was going to be messy. Yeah, we don't want any water on our keyboard. Yeah, in fact, I'll extend that to what's today's Tuesday. I'll extend it to Thursday because yeah, I mean, 2 reports and an exam all in the same week. That's kind of harsh. So I'll do that right after I sign off. So if there isn't any other questions, I will bid you a good day. If you do have questions about it, remember I respond to emails fairly quickly, and office hours are tomorrow, right? I can never remember. No, office hours are Thursday.
No, they're Wednesday.
Are they Wednesday? Are they tomorrow or Thursday? Tomorrow?
Tomorrow at 11.
Yeah. I mix up my 410 and my 210 class. I know one of them's Thursday and one of them's Tuesday. Yeah, because we have recitation on Thursday. So, right. So we have office hours are tomorrow. So if you have any questions, visit me then. Or just say hi. Anyway, have a good afternoon, everybody. I'll talk to you soon, okay?
Bye.
All right, bye-bye.